Okay, so for part two, now we're doing the chi-square test for independence/association. So basically, um, are they independent or dependent, right? Is there an association or not? So again, categorical data counts, right? So these are considered two-way tests, basically. And the next test, there's three tests total. There's goodness of fit, this one, and one more we're going to cover after this. This one and the next one are both two-way because obviously the table goes two ways, right? There's multiple categories, right? So there's multiple rows and columns, right? Okay, so here you assume there's no association, thus they're independent, or there is an association, thus they are dependent. So there's some variations in the wording there. Whatever the thing is, the noun. The expected is a little bit different because you have to do rows and columns and divide by table total. Sometimes it says like grid total or something like that, so it's going to vary. The degrees of freedom is number of rows minus 1 and number of columns minus 1. You just multiply that. So again, it's not the same as the goodness of fit as far as these formulas go. So let's say we collect data on patients and their treatment of non-blood related diseases from medical records. You want to know what is for this categorical variable for tattoo status and hepatitis D status, are they statistically independent, right? Having it, not having it, tattoo and hepatitis C. Is there some kind of relationship there or not? So you assume there isn't, and then you prove otherwise, essentially. So we're going to conduct a hypothesis test. So this is a chi-squared test for independence. So that's association, I guess. People vary on what they call it. I think this book uses association, but that's fine. Okay, so our hypotheses, H sub 0 and H sub A. Oh, that's not right. Try that again. Sub A. Okay, style. Text. Okay, so tattoo, that is not text. That is still math. Style, text, tattoo, status, and hepatitis C status are independent. We'll copy that, paste that, are not independent, thus you're saying thus dependent slash associated, right? Essentially. Oh, we got to do degrees of freedom. Degrees of freedom equal. All right, and then another set of parentheses. So here, if I look at the table, it's a 3 by 2 table. So 3 minus 1 and 2 minus 1. So I get 2. So that's my degrees of freedom. So I need a chi. So my area, oh crap, come on. My area equals chi squared distribution, right? Distribution. And we only do right tail for this because that's all we care about with the counts, the categorical data. So we need to get the chi value from the tables and then use the degrees of freedom, and that'll give us our p value, right? Because the area is the p value. All right, so that's where we pause there. Okay. I'm just going to copy this to make it save a little time here and put this into tab 2, right? Tab 1 we already did. Tab 2 we'll put here. Right, so if you think about it, this is really the observed, right? So we did a study, and these are the ones we observed, our samples we observed. Okay, I don't know why those aren't centered out like that, but that's fine. Okay, so I'm going to copy it again, and we'll just call these our expected, and we'll delete these. Oh, I got to make that bigger for the words. There we go. A little more. There we go. Okay, so we look back at our notes here. Expected is the row total times the column total. Divided by the table total. Okay. So we need to do equals the sum of these, drag it down, and equals the sum of these, and drag it over. So those are my row and these are my row, and we'll put a different color in them. How about what's a nice blue or something maybe? Who knows? So those are my totals there we need, right? And then my grand total, the sum of the whole grid, right? So there's 626. If you add up these, you get 626. You add these, you get 626. You add these, you get 626. Okay, so row times column divided by the total, 3.9, whatever the case may be, right? So you look at that, row times total divided by grand total, or table total. Okay, so row times column divided by grand, and row times total divided by grand, and row times total divided by the grand total, and row times, oh, I got that backwards, doesn't matter though. Okay, and then row times column divided by grand total. Okay, so we should be good there. So these should match up now. So if I do the sum here, I should get the same number, right? Same number, see that? And then the sum here, I should get the same number. Whoop. See that? Same numbers. Okay, so these are my observed, these are my expected. Okay, so now we want the components. I'm just going to put components. And we will link these two boxes together. Merge. Box it. And yellow. Bold. We want 6 of them, right? I'm just right-clicking to get that many. All right. So, components. Has it changed? No. The expected is different, and the degrees of freedom is different. But if I go back, the basic chi-squared is still the same, right? Observed minus expected squared over by expected. Add them all up, you get the chi-squared. Right? So that doesn't change for any of the 3 tests. Or 2. Okay. So, equals parentheses observed minus expected squared divided by expected. Okay, there we go. I can just drag that across and drag that down, and it does it automatically. So I click this one here. You look at it, it's going observed expected, right? Divided by, so it does it automatically. All right, so if I add all these up, equals the sum of all of those, right? That is the chi-squared, right? Right, so 57.9121, whatever it is, right? Okay, so we go back to here. We need to do 57.91, I think is what it was. Let me go back. 91217, comma 2, right? Because that's degrees of freedom there. Okay. Let's go back to our spreadsheet. So the area equals, okay, equals the chi-squared dot distribution right-tailed. Click on that, and degrees of freedom. And we get that, so that's a really small number, right? So that's 12 zeros and a 2 6, right? Because the decimal's right there, we have to move it over 13 times, so that's a 2 plus 12 zeros, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There's the 13th number. 6, I think, was the last number, correct? Well, I guess this, because I go out far, I don't even know. Doesn't matter. We'll put 2 6s. It doesn't really, it's not going to really matter either way, to be honest with you, right? As long as you know that's 13, basically, because if you look, that's a negative 13, so times 10 to the negative 13 in scientific notation. Okay, so essentially the P value, p value is less than alpha, right? Because again, this is the p-value, which is incredibly small, right? So I don't care what you picked here, because typically it's going to be 5%, 1%, 10%, something like that. Definitely going to be smaller than that, so we should reject the null hypothesis. Because the chance of a type error here is very unlikely. Not impossible, but very unlikely, right? Okay, so let's go back to our notes here. So there is enough evidence to reject the null hypothesis. The sample we found is significant. There is enough evidence to suggest that hepatitis, C status, is likely not independent of tattoo status. I only likes the capital C is the problem. Okay. We're not saying what the relationship is, we're just saying there must be some kind of relationship, whether it's more or less. Okay, so that's the independence test end of